Welcome to Dominic Does DIY. So this is a general purpose do-it-yourself channel, and today we're going to be talking about the engineering aspects of an operational amplifier, or as people like to call them, the op amp. So an op amp has many uses. It can be used as a buffer circuit, a non-inverting amplifier, an inverting gain amplifier, a comparator, a differential amplifier. It can be used as a peak voltage detector. It can be used as a transimpedance amplifier. It can be used as quite a number of things. But what we really want to know is, because a lot of these things can be found online, and I'll do another video on how each of these applications work in detail. But for today, we're going to look at the engineering aspect of it, where we want to see what is it that we're looking for in the op amp when we're looking at a spec sheet, because ultimately if we want to use it, we're going to want to understand what it is we're trying to look at. So for this episode, we're going to be using the LTC6244 datasheet for simulation and reference. To start off, we're going to have to take a look at we're going to have to pick an op amp. And so for this video, we're going to go ahead and take a look at the LTC6244 IC from Linear Technology. And this one is a pretty decent, pretty good op amp. Its main purpose is to be used as a transimpedance amplifier. So what a transimpedance amplifier is it takes a current and converts it to a voltage on the output. This is used in a lot of photodiode aspects, because a photodiode is considered a current source. And so it takes that current source and it converts it to a voltage source, which we can read with an A to D converter or something like that. So when we look at the data sheet, the first thing that we come across is the cover sheet. And the cover sheet lists some basic things that we need to look at and come to understand. This is their general values that they've given to this. It's the input bias current. So even though an op amp is supposed to have no current going into the pins in the N minus and the N plus, it does, since they are BJTs internally. A BJT requires a base current to operate, so there will always be some sort of input current on the pins. And of course, you want this as low as possible. And so this one has a 1 picoamp input bias current listed on the main cover page. That input bias current then also directly relates to the low offset voltage, or the offset voltage. And what that is just like you're not supposed to have any current going into the pins of an op amp in the N minus and the N plus, what also happens is, because you don't have any current going in, you should also not have a voltage differential between the N minus and the N plus. So whatever you have on N plus, you should have on N minus. But of course, because of the input bias current, you always end up with some sort of offset voltage, and this can be handled or mediated in a multitude of ways. And then we're looking at, and then the next thing on the list is the low offset drift. So all components, as you use more and more components on the engineering side of it, everything is affected by temperature. And as temperature changes, then critical specifications of those components change. So in this one, the offset voltage is a critical component for the op amp, and because of that, it lists the offset drift versus temperature in the main data sheet. So the next thing that we see on the list is the slew rate. And the slew rate is the rate of change in the op amp. If you remember from school, or maybe you're learning it now, but the slew rate is just how fast can the thing receive a signal and output the signal. So the higher the number, the better. And that slew rate is directly proportional to the gain bandwidth, right? So this thing has a 40 volt per microsecond slew rate, and its bandwidth is 50 megahertz. The other thing that it lists here is the output swings. So what this is the V out Some op amps have rail-to-rail, some have a limited output. So this particular op amp has an ability to go rail-to-rail. What that means is the output can go anywhere from V plus all the way to V minus and anything in between. You can also see it lists its low input capacitance at 2.1 picofarad. This is specifically listed here on the data sheet because, like I said, this is for a transimpedance amplifier. Now we will go ahead and scroll down. And you see here, this is the pin configuration of this particular op amp. Some op amps, there's two flavors that you can get in a pinout of an op amp. You can either get this one, which is just the basic V plus, V minus, right? Your VSS, your VCC, input, ground, whatever you want to call it. And then your in plus, your in minus, and your output. Some op amps also have a resistor. It is the input bias offset resistor. And so it'll have two pins, and you can put a resistor on there to try to balance out that input bias current to make your voltage offset 0. Instead of, like in this one, it was 100 microvolts. Right, so they actually have some op amps come with those offset pins to allow you to put a resistor to offset the offset voltage and make that voltage offset equal to 0 with that resistor. So as we continue to scroll down on the data sheet, so if you remember on the cover page, it was listed as the input offset voltage was going to be 100 microvolts. But now we get into some more details and we can actually see that the package makes a difference and also the temperature that we want to operate in. So that 100 microvolts is based on a 25°C ambient temperature as listed in the electrical characteristics in the main. It says it is otherwise specifications are T sub A equals 25°C. And so that 100 microvolt max is based on a 25°C environment. If you're going to work outside that range and you want to work in 0 to 70°C, you can see that that offset voltage goes to 225 microvolts. And if you want to work from minus 40 to 85°C, it goes up to 300 microvolts. So you have to take into consideration of what is your working environment, like what temperature ranges do you plan on operating in. You can also see there's a big difference in the package type. So the MS8 package versus the DD package, even at 25°C, you can see that the MS8 package has a much lower offset voltage at 100 microvolts versus the DD package at 650 microvolts. So package also is a contributing factor on what will be that offset voltage and some of the specs. So another characteristic that we want to take a look at is our RN and our CN. So these two may or may not be pertinent to you. It all depends on what you're using this particular op amp for. Like I said, this one is for a transimpedance amplifier specifically. So in these instances, the RN and the CN are critical to determine what it is that you want to do, because they will directly affect the photodiode and its operation and its ability to detect a signal. We actually have some more universal general purpose specs that we need to look at for the op amp. The first one is this VCM. It's the input voltage range. So even though the output is rail to rail, that does not necessarily mean that you can put rail to rail on the input pins. The input pins themselves have a specification VCM, and this is on this part 0 to 3.5 volts. That means that you cannot go over 3.5 volts on the input pin. Even though this is a 5 volt rated part, you can put 5 volts on the V plus and ground on the V minus. So you have a 0 to 5 volt rail to rail. You can only go 0 to 3.5 volts on the input pin. So here you can see they're listing the gain bandwidth and the slew rate. the gain bandwidth. They listed as 35 to 50 megahertz, and the slew rate when it's going through a -2 gain amplifier is only going to be 18 to 35, and this could range, the range on this is basically from their lots of the components. So even though they listed at the top of the data sheet 40 volts per microsecond, the reality is when you start going across chips, it is not that consistent. So you can have anywhere from 18 to 35 volts per microsecond across a variety of chips. When you get like a handful of 1,000, there's no guarantee that you're going to end up with the same volts per microsecond per chip. And then as we continue to go down, they'll list all these specs again, because as things change, as your VCM changes, as your VS changes, as all these things change, the parameters and the output specs also change. So you have to be considerate. You have to consider what it is that you're doing, what application you have, and how you're going to use this. So now we will go ahead and take a look with all these specs in mind. How do these affect each of the outputs of the op amp? So now that we've seen the data sheet and we know some ideas of what it is that we want to look for on our spec sheet, now let's understand how each of those things affect the output circuit. So I'm just going to run through some simulations. I'm using LTSpice if you want to pick it up. And like I said, we're using the LTC6244 op amp. And so what we're going to start with is we're going to go ahead and put two voltage sources. This is going to be our 5-volt rail. So our VCC as a DC power supply, and then we will create a sine wave. So this one right here, I've just got it set up. I didn't go into advanced. I just need a DC power supply for our VCC rail. So I just gave it a value of 5. This one right here, I set up as our sine wave. The AC amplitude, I just put as 1. This is if we wanted to do an AC transient, which we will not do in this video. I gave it a DC offset of, we'll change this. So we'll make our DC offset 1.75 volts. Our amplitude, 1.75. We will run it at 10 hertz. And no delay and no phase shift. And we'll just run it for 2,500 cycles. So that is now our sine wave. That should now give us a sine wave from 0 to 3.5 volts. Because remember, our VCM is 0 to 3.5 volts. So we will take in that entire input swing. Our output is 5 volts to ground. We've got our ground here, and we got our 5 volts on our VCC. So this right here, we're just going to look at the buffer circuit first. And our simulation, if you go up here to the simulation, we'll edit our simulation profile. And because it's 10 hertz, we will run it for 1 second. So now we will go ahead and run this. And remember, we're going to be looking at our op amp, our input is going to be the sine wave. It's just a buffer circuit. So remember, our N plus equals our N minus. So since we are going to be altering this N plus, everything that we put on the N plus is going to be mirrored to the N minus, and then it's just going to go to the output to this buff out, our buffer output. So let's go ahead and run it. And you can see here, our buffer out. If I also monitor the input, they are in phase 1-to-1, no real difference on it, right? Whatever comes on the input, we see on the output. We want to see what happens, right? Remember, this thing has an input range of max of 3.5 volts. So now we want to see what happens if we adjust our thing. So instead of going from 0 to 3.5 volts, right? Or to 3.5 volts, yeah. So instead of going from 0 to 3.5 volts, let's just crank it up 1 volt, right? And so we will go from, so instead of 1.75, we will do 2.75. And so now what this will do is this will now shift us up it'll DC us off, offset us up 1 volt. So now instead of 0 to 3.5, we'll go from 1 to 4.5, right? So now we're going to go over that VCM limit, and let's see what happens in that regard. So let's go ahead and run the simulation again. So what do we see happening here? We can see that the input, because our input exceeded the VCM, it was no longer doing what we were expecting it to do. So even though our input was going from, as we said, from 1 volt to 4.5 volts, just as expected, because we exceeded that 3.5 volt VCM, we could not get the output. Even though the output was rated up to 5 volts, because we violated the VCM, we went over the voltage of the input, we could not see that translate from the input to the output because of that violation, because of the VCM violation. Right? So we want to make sure that our inputs are always below the VCM range, so we make sure that we get the output that we are expecting. So now let's go ahead and revert back to our original. That was working good. So we'll just run it one more time just to verify. So 1 to 1. So now we're going to go and check and see what happens when we increase the frequency, right? The slew rate. Because right now at 10 hertz, our slew rate is really low. Right? We don't need we do not need a really impressive slew rate to handle a 10 hertz signal. So remember, this part was rated for 40 microvolts on the cover page, and then when we looked at the specs, it was like 18 to 35. So let's go take a look and see what happens. Let's just try to go to that 35 volt per microsecond rating, and let's set up a signal for that. So in order to get the 35 volts per microsecond, we have to figure out what is our frequency got to be. What do we have to have that frequency? So we know that our signal goes from 0 to 3.5 volts in one swing. So we need to get 35 volts per microsecond. Right? So how do we do that? Well, we have a 3.5 volt signal that we're putting into the system from low to high, and we have to get a 35 volt per microsecond, so we divide that by the 35 volts per microsecond, and that gives us 0.1 microseconds. So we need a transition of 3.5 volts in 0.1 microseconds. But of course, that's just, when we're talking, that's just one upswing, and we want the whole period. So a period is an up and a down. So that's going to be 0.2. So what does 0.2 come out to? 0.2 microseconds as a period. 0.2 microseconds as a period is actually 5 megahertz as a frequency. So we're going to go ahead and change our frequency to 5 megahertz. And then we're going to go ahead and run that. And now we should be up to 35 volts per microsecond, which is pushing the threshold of what this part could do. So in addition to changing the frequency, we also want to change our transient simulation time, because we are now going a lot faster. We do not need 1 second of data. It's just going to look nasty. So we're going to go ahead and change our simulation profile. So instead of going 1 second, we're going to go ahead and reduce that to 5 microseconds. And let's go ahead and run that. So here we can see, even though we went with the 35 volts per microsecond with that part, and this should have been able to handle it, we can see that we've got a reduced output from what we're expecting, because it's a buffer, so whatever goes in must go out. But we're not getting that. Second, we're also seeing a phase shift. So the part cannot react as quickly as we would like it to. So we can see that the slew rate isn't what it was listed as, 100%. So the question is how fast can this thing go, right? Let's just reduce it down to 1 megahertz and give that one a go. So you can see with 1 megahertz, we have a pretty good input to output capability. With this voltage swing, there's a slight distortion here at the lower end, but other than that, it is pretty good input output visual, and would probably work good for most circumstances. However, if we start going up even to 2 megahertz, and we run 2 megahertz, you can see we start beginning to get some distortion, right? We haven't violated the input, but you can kind of see that our output is going higher than our input. So we're getting some slight gain amplification here in the system at this frequency, which could be a byproduct because I do not have a gain on this. It should just be input to output. So there might be something with internally on this op amp, which is causing this anomaly of having this gain amplification going. And if we even go up all the way to 10 megahertz, which will really violate everything, you can see that we barely can even operate, right? Like we're not even going from 1.2 as an output, 1.2 to 2.4 volts, with still that 90-degree phase shift going on. So basically with this setup, we don't want to go over 1 megahertz. Is about as much as we want to, as fast as we want to go with this setup. So now what we're going to look at is we're going to take a look at our output voltage levels, right? Because our output voltage levels, remember, we could still go rail to rail on the output so long as we don't violate that VCM. So how do we get a higher output? How do we get a higher output than on the input? We got to use an amplifier. So what we're going to go ahead and do is instead of using this buffer circuit, what we're going to do is we're going to go ahead and use the non-inverting gain amplifier. And so what this does is it gives us a gain of 1 plus RF over RG, right, which is our feedback resistor and our ground resistor. And I've got a parameter based setup here going on. So let me just go ahead and I'll move that over here. And so we should have with an RF of 44 and an RG of 1, that gives us a gain of 44. So now in order to use that, we're going to go ahead and change our source. And because we can't use this, because a gain of 44 is going to be way too high, we're going to go ahead and want to drop this down to a 50 millivolt source and a 50 millivolt swing. So now this will give us so what will this do? It'll give us now a 0 to 0.1 volt sine wave. And we got a 44 gain. So 0.1 volt times 44 equals 4.4. So we should be able to see on the input 0 to 0.1 volt. And then on the output, we should be seeing 0 to 4.4 volts on the output. And we'll keep it at 1 megahertz. So now we're also not going to be monitoring the buffer out anymore. We're going to be wanting to take a look at the non-inverting AV out. And so let's go ahead and run that. So now you can see our input voltage is going from 0 to 100 millivolts. And our output voltage is going from 0 to 4.4 volts. There's also a slight shift on it. We ended up with a little phase shift going on. Looks about 90 again. So we can get a better idea of that offset voltage down here because it's very hard to see. What we'll do is we will adjust our input. So instead of looking at 50 millivolt input, we'll go down to a 5 millivolt input. All right, so we're going to shrink our signal down a lot. And now we will run it. And so you see here, now we're getting closer. We can see that at about 150 millivolts, right? We can see that there's an offset voltage that's happening here. There's this lower limit that we just can't, even with 0 volts on the input, nothing's happening. And if we really wanted to do it, we could just say, take this guy and go to none, and then just do a 0 volt. And then what's our output? So with nothing on the input and a gain amplification, actually let's go ahead and take our amplifier and we'll make it a unity gain amplifier also. And so you can see that our output is about 1.2 millivolts, right? Based on the calculation that they're doing here for the simulation. So that's the voltage offset parameter. So the spec sheet said that it was about 100 microvolts, depending on what the thing is. They may have done the specs on the DD package, because if you recall, the DD package was a little bit closer to the 1 millivolt. And they may be doing it at ambient temperatures or elevated temperatures, something like that. So, but you can see it here. And so if you try to do simulations with that, where you're trying to do too much of a high gain, that offset will mess you up. Let's take, for instance, let's go back down to our sine wave. We'll throw in our 5 millivolts again. So 5 millivolts give us our 10, right? And we'll just keep it at the 1 mega. Bring up our 2500 cycles again. Right? And now let's just crank this gain up. Right? We're going to violate some stuff. In all honesty, we should, with this value, we should be able to see in the perfect world. This should then take us from 0, right? If our output was 0, if our input was 0, offset voltage was 0, everything was good. This is a 4400 gain amplifier. And so we may have to actually adjust our sine wave input. Let's bring up our calculator again. So we don't want to go above 4.4 volts. So divide that by 4400 gain, 1 millivolt. Right, so let's go back to our sine wave, and we want a max of 1 millivolt. So we will just put just make that 0.5, 0.5. So that'll give us a 1 millivolt, 0 to 1 millivolt swing. Right, and now if we run that, you can kind of see we got our 1 millivolt swing like we expect, right? And our input reaches 0, that's not a problem. Our 0 point is all the way up at 4.95 volts, right? And so you can see what happens with the high gain, that voltage offset, what it'll do. So you want to watch out for that voltage offset, because then your gain amplifier, depending on how big of a gain amplifier you want, may have adverse effects. So through these simulations, we've seen that the op amp and these parameters and how they affect it. We've seen the VCM, right? We've seen that when it says 0 to 3.5 volts, if we try to go above that input voltage, our output does not reflect correctly because we've exceeded that VCM. We've also seen the output rail to rail. We've been able to see the rail go up to 5 volts so long as we stay true to that VCM and don't go above that. And then we also saw what happened when we tried to exceed the slew rate capability. We saw phase shifts. We saw outputs that were not fully gained, right? Because the slew rate wasn't fast enough. So we got to make sure that we stay, whatever our application is, we got to stay under that slew rate. We got to stay under the VCM for the inputs. We got to maintain our output parameter, right? This was a rail-to-rail one, so we could go all the way to 5 volts. But the same thing that we saw happen with the VCM, where we exceeded the VCM on the input, it didn't give us our output. The same thing could happen if the output is not rail-to-rail. If you tried to output something that was greater than that, then we would not see it, right? So just keep those things in mind. But so long as you stay within the specs of the op amp, so long as you stay within the spec of the inputs, the outputs, and the other ratings, the slew rate, don't try to process a signal faster than the op-amp can tolerate, then the op-amp is a great tool to use in many different applications. And we'll get into some of those applications later. But until then, thank you for watching.